All right. Good morning. It's now 5 a.m. So I'm up very early, but let's try and compete in this Code Forces round. Round 657, Div2. All right. Acacius is studying strings theory. Today he came up with the following problem. You have a string of length n consisting of English letters and question marks. You can make question marks lowercase letters, and you want abacaba to occur exactly once.
For you, sir, always. Understood, sir.
Well, the exactly once, I guess, is the confusing part. But we can make everything z except for the one instance of abacaba. Yeah, okay. So let's try that. So we want I plus 7, or I plus 6. So less than this. Yeah, okay. So and works equals false. Works Alright, so we can just like try each position now. Alright, so now we'll go through each character. If word at start position plus I not equal to a question mark, and it's not equal to abacaba at I, and try again. Otherwise it works, so that means that word at I equals abacaba at I. Okay, and now if it's a 0, we need to fill it in. So word at I equals Oh. I need to make a thing. Okay, so we have this thing that we're making. If it's a question mark, we set it to 0 or to a Z. Otherwise, we set it to, where did I? Okay, so now we've made this thing that we're interested in. So now if works created, then sysout created. That would do part of it. So we need to read this in. Okay, so here we need to print yes. So one issue. Also here we need to print no. It's taking me a very, very long time. What is this? This should be plus I. Yes, abacaba, yes, no. Okay. Sounds good. So, I don't know, I wouldn't say that's a good performance, I guess, on problem A. But I'm also up very early, so I'll use that as an excuse. Wrong answer, pretest A. What?
Problem A. Wrong answer. Test 1, sir.
This one I say no for, but the answer is yes. It appears. Take test case 3. You can do abacaba, but I can't. Well, this should be yes. Zero, 1, 2, 3, 4. Yeah, okay. So now that's fine. Created, oh, there you go. Start position plus I. Okay. Good. Well, thank you for the good samples, I guess. Problem B. Wrong answer pretest 2.
Problem A. Wrong answer test 2, sir.
Can I not type? Each question mark should be replaced with exactly one English letter. This can be transformed into this or this, but not this or this. Exactly once. So it's harder than usual. Usually A is a lot easier. But I think my idea is right. So we have this thing that we're going to create. Oh, this seems wrong. Yeah, it's got to be that. Yep, that's important. Well, I was creating the array, but I was creating the array and then overwriting parts of it. So like it wasn't 0 as I expected it to be. So I was only really trying to place Abacaba in like the first position. Otherwise I might place too many of it. Anyway. Pasha loves to send strictly positive integers to friends. Pasha cares about security. Therefore, when he wants to send an integer n, he encrypts it in the following way. He picks 3 integers a, b, and c, then computes the encrypted value m equals n times a plus b minus c. Well, b and c could just be one integer then, right? Seems pretty unnecessary. Unfortunately, an advisor has intercepted the values of L, R, and M. It is possible to recover the original values of A, B, and C, or is it possible to recover the original values of A, B, and C from this information? More formally, you ask if there are any. Okay, so we have the input and the output. We also have B and C. A, B, and C. Well, it seems to me we brute force n and then check which B's and C's work. We brute force A rather. Yeah, if we know what A is, then we know the max of B minus C that can be, and we also know the min possible B minus C. So the max possible B minus C, the min possible B minus C. And we know how big the range is. More formally, we have to find any values A, B, and C that work, not how many that work. Well, same solution idea though, I think. Oh, oops, I had this really small. Apologies, I was coding not in front of a camera or other people. So that's why it was small. Should be fixed now though. Oh wait, we don't have an n. I thought we were given n. We're not given n. Well, then I guess we could brute force the smaller of n and a, right? Because that's going to be relatively small. Okay, so int n equals 1. Well, let's try this again. Int m equals this first thing. Alright, so for int a equals 0, a is less than, or a is at least 1, presumably. Yeah. A is less than or equal to m, or a times a is less than or equal to m, a plus plus. Good. Okay, so this is all possible a's, but now int oa would be m over a, because like that's the other possible legal thing, which is now long. So if m mod a is not equal to 0, continue. If a is less, okay, well, so boolean a works equals a is greater than or equal to l, and a is less than or equal to r. We also need the OA works. This is the same thing, but with OA. So if not A works and not OA works, then we have no A candidate. Otherwise, we have the candidate for A. So now in target difference, yeah, that does not help at all. All right, that's unhelpful. So try again. Let's go from L to R. So we want to go between L and R. The reason this doesn't work is because you don't have to actually multiply to M. You might multiply to anything. Like you might multiply to above or below M. So now we know that A works. So now there are two possibilities. We can either go just below the target or just above the target. So int below times will be equal to M divided by A. Below times A. Above is above times A. And then we also need to keep track of what this n is, right? Or does it need to be positive? It's an integer n, so n I think can be 0. All right. So int below difference equals m minus below. If this is less than or equal to r minus L, then we have our answer. So then we sys out A plus a space plus the bigger of these will be R plus a space plus the smaller is R minus below difference. Okay, otherwise we can check if above minus m less than or equal to r minus L, then A L plus above minus m. I think that is fine. Because we add B, subtract C. This will give us something negative. And continue outer. What if it's not possible? It's guaranteed there are at least one possible solution. 4, 6, 5, 2, 3, 2. Uh-oh. Those will give different answers, won't they? Since n is strictly positive. I see. And below times greater than 0. Yeah, I think that's fine.
Well done, sir. I see you on problem B.
Alright, problem C. Vladimir would like to prepare a present for his wife. They have an anniversary. Yeah, that makes sense. Vladimir went to the flower shop. He was amazed to see there are n types of flowers being sold there. There's an unlimited supply of flowers of each type. Vladimir wants to choose flowers to maximize the happiness of his wife. He knows that after receiving the first flower, the ith happiness increases by AI. After receiving each consecutive flower, it increases by BI. That is, if among the chosen flowers there are this many flowers of type I, his wife gets this many happiness. Please help Vladimir choose exactly n flowers to maximize the total happiness of his wife. So the only thing that matters is average happiness. But the average happiness can decrease over time. Yeah, like the average happiness decreases over time if BI is less than AI, which is not necessarily guaranteed. Seems unusually difficult for Div2, to be honest. But maybe it's just unusually early. Oh, the delta is simply, I guess the average doesn't matter at all, really. You can kind of just make greedy decisions. Well, alright, so the n squared I think would be fine. Oh, it's n and it's big. Yikes. So there's one flower. Yeah, okay, I think I see how to do this. So there's one flower you're gonna buy almost all of the BI from, because there's no reason to split your BI choices. So you're gonna choose, other than like the first flower of each type, the second one you buy from each, like you're only gonna buy one flower more than once. Every other flower you'll buy 0 or 1 times. Then the flowers that you buy once are the ones better than the second one's B. But if it's worse than the second one's B, you'll only buy it once. So if we sort the things by A, then some suffix, you'll buy all of the A's. Then we can calculate the B values for it. That's the idea. Comparable flower. So yeah, we just want to sort by A, and then I'll sort them in reverse order to make things easier. I think also it's helpful to have a used array. Probably, I guess. And then we should read in all the flowers. Oh, we need to read in M as well. Okay, so now we're gonna need a cumulative sum array. I think it won't hurt at least. Okay, so then CS at I, CS at I minus 1 plus flowers at I minus 1 dot A. Okay, so now we'll do our sweep, and then so this I will be the one we take lots of. So then yeah, okay. So while flower index is less than n types, and flowers at flower index. Oh wait, we also want to sort these by B, huh? Yeah, okay. Oh man, how do we... Okay, so we can't just do a comparator here, like a lambda, because you can't do lambdas with arrays.sort for some odd reason. Or maybe that's just arrays.sort with primitives. Maybe you can with objects. Oh well. Okay, so now we have both of these arrays sorted. So while this flower A is less than flower B sorted at I.B, then flower index plus plus, and also flowers at dot A equals true, or dot used is true. All right, so now we have the number of things we would like to use. So int real by will be equal to math.max of 2 by so we want to buy this many, well, max is 0. 2 by minus flower index. Yeah. Should be n by. So that's how many we would like to buy. Let's case this out. So if flowers at flower index, or at oh wait, what is this? This is really B sorted. If B sorted at I.used. So we know we want to buy this thing. Well, we can just, let's special case out if we can't even buy all of the A's we want. So if we can't even buy all of these, then canned is just going to be equal to this many cumulative sums, like this many good flowers sorted by A. And then we're fine. Otherwise, we have to figure out what canned would be here. And now best equals math.max, best of canned, and then just print it. Good. Okay, so now if we use this, we have one case, otherwise we have another. So if we use this as an A already, then this is how many we'll actually buy of the second type. Canned equals real buy times b sorted at I dot b plus cumulative sum at flower index. Otherwise, we need to add a couple things. So plus b sorted at I dot a. So we buy the first one. We also buy one fewer of these things. Then we also buy everything we want. I think that's fine. It is not fine. So you buy 5 and then 2 of these, I think. 5 plus 9. What is 5 plus 9? 5 plus 9 is 14. Interesting case. How do I get it wrong? Oh, as should be greater, first of all. Second, the b values we want sorted in decreasing order, so that they get, yes, that the a values get less or get more and more required. So that was at least 2 mistakes.
Well done, sir. AC on problem C.
All right. Good to see some people doing it. New passenger trams. There are many freight trains departing from this planet every day. One day, that planet consists of 8 hours. Each hour consists of this many minutes, which is even. Currently, there are n freight trains. They depart each day at the same time. The ith train yeah, skipping A is understandable. It was hard, man. It was a difficult problem, especially for this early in the morning. The ith train departs at h hours and mi minutes. Do I understand that? Yeah, I think I understand what's going on. The government decided to add passenger trams as well. They plan to add a regular tram service with half-hour intervals. That means at 0 and at m/2. The second tram departs halfway between the hour after the first one, and so on. see. So like it's any 2 times an hour. Got it. To allow passengers to board the tram safely, the tram must arrive K minutes before. During that time when passengers are boarding the tram, no freight train can depart from the planet. However, freight trains are allowed to depart from the very moment the boarding starts, as well as the moment the passenger tram departs. Notice that if the first tram passenger departs at 0 hours and T minutes, freight trains cannot depart during the last that many minutes of the day. So there's like some window that gets blocked off. Unfortunately, it might not be possible to satisfy the requirement of the government without canceling some of the freight trains. Please help the government to find the optimal value of T to optimize the number of canceled freight trains in case all passenger trams depart according to schedule. I see. Can we not? We only care about the value mod h over 2, right? Why are we splitting? Do the different hours even matter? I don't think they even do. Yeah. Like, this seems kind of unnecessarily convoluted as a problem statement. I've got this n, which means there are this many what? This many freight trains, this many hours, and this many minutes. And what is K? K is, oops, excuse me. K is the length of the window. Minimum number of trains that need to be canceled, and the optimal starting time T. Is the starting time in the beginning of the window or the end of the window? So it's the ending time T really, rather, but that's fine. So we need to find, yeah, okay. So slide the window over until, yeah. Man, if only I had ordered set in C++, this would be very easy. Instead, I'm gonna have to write a segment tree in order to deal with these 10 to the 9th coordinates. So I want segment tree and range sum. That's it, with an implicit segment tree. Yeah, so this problem would be like way easier in C++, but I think that's fine. 24 hours a day, 60-minute hours, 15-minute blocks. So they happen once an hour, right? 2 per hour. Okay. So these hours don't even matter. So we just have a 0 and a 15, which means, yeah, we have a 15, whatever, we have a block of 15. seg tree. Okay, and now we want to make the kids whenever we have a query. Public void range. Oh, what else? What information do we need to store? The sum. Yeah. Okay. Public void recalc. Anything else? Public void update. So make kids, and then if well, if leftmost equals rightmost, then sum plus plus and return. Otherwise we make our kids, and then if index less than or equal to lchild dot rightmost, then lchild dot update. Otherwise rchild dot update. What does this do? So int mid equals leftmost plus rightmost over 2. Lchild equals new seg tree from leftmost to mid. Rchild equals a similar thing. Okay, so we've got our kids made. Recalc, yeah. So if leftmost is equal to rightmost, then we're a leaf, so we can return. Otherwise, if lchild equals null, then sum equals 0 and return. Otherwise, sum equals lchild dot sum plus rchild dot sum. So after we update, we want to recalc if we aren't a leaf. Now we need a query, public int query, L and R. If L's less than or equal to leftmost and R is greater than or equal to rightmost, return sum. L is greater than rightmost or R is less than leftmost. 0, return lchild dot query, then otherwise make kids, return lchild dot query plus rchild dot query. Good, okay, so we have that all done finally. Okay, so now we need, this is int n trims, this thing, or I guess they're trains really. We don't care about the number of hours. Int min equals this over 2. So then we read in each of the trim information parts. Yes. Tree 0 to minutes. Is it just 0 to minutes? Any other information? Yeah, what else do we care about? Zero to, let's just keep it like this. Yeah, I think that should be fine. Times 2 minus 1 really is all I'm gonna need. Okay, then 4 I equals 0, I is less than n trains plus. We don't care about the hour, int minute equals this thing. Yeah, so we have some length that's at most minutes over 2. So this can just be this. st.update minute by 1. Also st.update minute plus minutes by 1. Plus minutes over 2. Okay. We should also probably keep a list of start times. Into length as well. Okay, so minutes plus 2, right? So that way we include, like if minutes is 3, 0, 1, 2, 3, 4. Yeah, include all of those. Start times dot add. Best ants equals integer dot max best time equals 0. Alright, so now we want to try each possible start time. If there are multiple answers, print any. I'll assume that's the case. So for each start time, then int to cancel will be equal to st.range query from I to I plus the phase length. To cancel less than the best answer, then to cancel, then best ants equals to cancel, and the best time will be I. So we have an issue here though. Minimum number of trains and the optimal starting time T. Yeah, it's kind of weird that it's the it's like the beginning of the range rather than the end of the range. So this is best time plus k mod minutes, I think. Yeah, okay, I think this is fine. 0.15. Well, that would work. But we should print 0. Oh, I guess these are two different choices. Yeah. The first tram can depart at 0 hours and 0 minutes. The freight train at 16 hours and 0 minutes. Can depart at the same time, and the freight train at 17 hours 30 minutes can depart at the same time for the upcoming train. Yeah, I think that's fine. So I say 016. The answer is this. Freight trains that need to be canceled. Oh no, that's annoying. Why would you say that? This query is wrong. So this needs to be fixed. But also it's not returning the right value, which means something else is wrong. Unfortunately. The next lesson equal to the left child's rightmost, then update the left kid, otherwise update the right kid, and then recalculate our own answer. Query, if left is less than or equal to leftmost and right is greater than or equal to rightmost, return sum. If left is bigger than rightmost or right is less than leftmost, return 0. Seems fine. Make kids and return their sum. I can't write a seg tree. Oh man. Okay, updating index 0. So the trims happen at times 0 and 30. That makes sense. Oh, 0 and 30. Yeah, and then also 15 and 45. That should definitely not be that. What is going on? Querying 0 to 16. Well, we've updated 0, and we also updated 15, so this should definitely be 2. Now the query is wrong, but it should still be 2. Yeah, okay. I think that makes sense. What am I doing that is wrong? So we update 0, 15, 30, 45. Oh, make kids. Yeah. If child equals null. I think the last time I wrote an implicit segment tree, I made the same mistake. Okay, 216. Okay, so that's one problem. Second problem is the following. It should be +1. It should be -1. So now we should say 1, but not which one. Or that's a useful debug statement. Okay, now we have to say which ones. So we need an array list of start times here. Okay, so now start times dot get I and L equals best time. R is equal to best time plus phase length. So if start, well, t equals start times dot get I. So if t is greater than L and t is less than R, then it's out I. It's all in one line. Second line, okay. Okay, so we need to print it then. We also need to print it if this is true for t plus phase length, or t plus minutes. Yeah. 116, 1. That should be equivalent, I think. No, it's not. It needs to be 1 indexed. So now my answer is 0. So if it's 16, then it goes from 0 to 16. Yeah, okay. Why is their answer also 0? Oh, theirs is very confusing. Okay, I think, yeah, that happens to be fine as well. They just end at that time.
Problem debugged. Wrong answer. Test 3, sir.
Really? That's kind of annoying. I don't know how much I like that. Okay. Well, this should be fixed. And it's +2. Yeah, that should be fine, I think. Now we have a seg tree from 0 to minutes minus 1. Minutes minus 1. Yeah, that's the problem. Yep. Okay. So how does this work? So maybe what does input format look like? So maybe it takes 30 minutes. And we've got like a third train that runs $18, $31. Well, this is just very wrong for all sorts of reasons. Oh, no, it's not. You can keep one indeed. 32 though. Okay, that's fine. But what if it's like, oh, how big can the phase length be? K is small enough. maybe that's not an issue then. I don't print 3 things. Plus minutes over 2. Yeah, that would do it. Wrong again.
Wrong answer, test 3, sir.
It's unfortunate. Now why would it be wrong? This shouldn't actually matter, because we know it's always smaller than minutes over 2. Do we know that actually? Let me triple check. Less than or equal to minutes over 2. Yes. So you can always let at least one freight train through. Minute plus minutes over 2, blah blah blah, add the minute. So now we have whatever this best answer is. We have our best time. Is it always true that it starts at a given thing? Might not be. Might end at a thing, right? Is that the case? Well, we have some optimal range. Move it left. Till eventually someone leaves or it starts at someone. So yeah, I think this is fine. I think we only need to check. The only start times are right after something happens. Because if you have any time, you just slide it left till you're about to include someone else, and then you just don't include them. So you can have any optimal answer here by checking these things. So we're checking enough, I think. It's better than the best answer, which it always is at least once. Good. Now we extract them. Mm. This is the segment tree fine. Update. So increment your sum if you're ever updated. Do we ever update anything sketchy? It's minutes minus 1. It's the biggest it gets. This should be fine. So cancel from 1 after this minute to 1 before I plus phase length. Yeah, that's fine. If the thing to cancel is less than the best answer, or if the number to cancel is less than the best, then this is our new best, and this is our new best time. Print the best answer. Print the best time plus the phase length. Is this going clockwise or counterclockwise? What does the optimal starting time mean? I'll ask you a question. Just strikes back. Unavailable cells can become available again, and in the easy version they can't. Okay. Like chessboards, they invented a game. Field is a chessboard 2 by n by 2 by m. It's 2 n rows, 2 n columns. The cell in this row is covered as white if this is even. Okay, otherwise it's black. Proceeds as follows. He marks some of the white cells unavailable and asks Ivan to place this many kings on the remaining white cells in such a way so that no two kings attack each other. A king can attack each other, blah blah blah. If you'd like to explore different combinations of cells, initially all cells are marked as available, and then he asks queries. In each cell he marks one unavailable. After each query, he would like to know whether it is possible to place kings on the available cells in the desired ways. How many kings do you place? Wait, what? How many kings is he placing? Asks Ivan to place n by m kings. So how many squares are there? There are n times m squares initially. Now some white squares are unavailable. Now you have to place kings on the remaining white squares, but there are fewer than n by n of them. What? I don't understand it all. So initially, if it's even by even, then half of each column is white. Oh. So initially there are n times m times 2. Yeah, okay, I see. If you're speaking about the picture, then yes, T matches with the end of the red range. So I'm just wrong. Okay. So for this problem, we can binary search it. You cannot for F2 though, presumably. Yeah. So we can make it so the kings can only move up, left, down, and right. Because that's like pretty much what's happening. Like there's not really a reason to make the problem this complicated, I don't think. So now, if a king can move in 4 directions, we need to see, like for some board, when can we not place on half the pieces? And we always can. We can always do half the pieces. Because we can always do, oh, we can always do all of one color. That's cool. Is that the only way to do half of the pieces? That is the only way of doing it. Brilliant. This is such a slick problem. I plus j is even. Yeah, that's super cool. Well, let's do that then. Int n on white equals 0, n on black equals 0. Or int equals 0 less than k. So one of the squares needs to be empty. Otherwise it's impossible. Neat. Okay. So int x is this, y equals this. Can we make a grid that's actually that big? We can't. Darn. Okay. Static. Oops. Spec. Limits comparable. So now Boolean white is the next thing, right? So it is white if, well, okay, int comp x equals x plus y, int comp y equals x minus y. So we know x plus y is even, they said, right? So the parity matches. Parity matches, which means this we can divide by 2, this we can also divide by 2. So now, return comp x plus comp y on 2 is 0. Good, okay, fantastic. Points that contains p, then delta equals -1, points that remove p. else delta equals 1 points dot add p. Okay, now if p dot white, then n on white plus equals delta, else n on black plus equals delta. And then after each query, sys out n on white, well, math.min n on white is equal to 0, yes, no. I never read n times m. Does that matter? Really, that doesn't matter either. Brilliant. What's going on? Hello. One test case, thank you. Yes, yes, no. Oh, I feel so smart having solved that. Although I realize I'm not really actually that smart having solved it because it wasn't at all a hard problem and chances are nobody's just reading it. But it's clever.
Problem F1 got wrong answer test 7, sir.
Oh no. Why would that be? How could you possibly? Oh, width times height could be yeah, width times height could be odd. So what does this map look like? 0, 0 will be 0 plus 0 over 2 and 0 minus 0 over 2. So width n and m do matter. somewhat at least. So you can have you have this star looking thing. You need to place 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What would this look like for real though? Have a width of, or a diagonal of 5. So 3 by 3, it looks like. Yeah, if you have a 3 by 3, board, or wait, what would that be? Would that be so 5 by 5? Let's get 2 colors out. So we need but it's got to be even by even. So this can't ever happen. Then you can do this, 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 this. Yeah, okay. So it still might be possible. So we've got a break case for that. It's finally getting light out. Let's see. So I wonder, is it, well, strategy-wise, what do we do? Strategy-wise, I think going for F might be, well, it's a little bit of a gamble, right? Like, everybody, oh my goodness, everyone is getting D. So D is slightly more safe, and I think F is the gamble, and I haven't even read E. Let's spend a couple more minutes on D, because I should be able to get this. I definitely know how to write a segment tree, and I know how to do a query. And I think that's it. I'm sure somebody's looking at this thinking I'm an idiot for not seeing whatever obvious bug there is. It's like, can this overflow maybe? Do I have overflow issues? Let's think about that. Because I might. These should both be smaller than 10 to the 9, so this should be fine to add them. So why am I wrong? Alright, well, that was the time that I wanted to spend on D. Let's figure out F now. We need to find whether this is monotonic. So if there are ever any matched pair where both are illegal, then it's impossible. If there are ever a like bottom right that corresponds to, so there's a bottom right, if there's a top left, that means all of these need to be free. And also all of these need to be free. Really, this entire section needs to be free. I see how you would do it. I don't have time. But what you could do is you can maintain a monotonic chain, and then you either care about the first, like you're either constrained by X or constrained by Y, which means there are 2 points in the chain that are interesting to you. Yeah, good problem. It's cool. Yeah, you keep a monotonic chain. Oh, how do you remove from the monotonic chain though? Things might get deleted. That seems very difficult to do, actually. I don't know how to do the problem. Well, nice job to Seba. I guess the only choice we have now is to fix D. In hindsight, I guess if I just binary searched F, that would have been a very good idea. Getting D, binary searching F would have been a decent placement for me, I think. So that's the better strategy. Oh well. Hindsight is 20/20. Okay, maybe I just run cases. For things, number of hours doesn't matter. Let's say they're 4 minutes. Can the number of minutes be less than 4? What if there is 1 minute? What does that even mean? Wait, what if it's 2 minutes long though? Oh, this could be a problem. I think that's what would happen. Yeah, if it's 2 minutes long. No, it's not right. I had it right before. If it's 2 minutes long, the only time that's illegal is the time. It's like the start plus 1. Alright, so back to the cases. 4 minutes, what is this last thing? Probably a useless number again? Oh, this is the length of the thing. So this is, let's just make this 2. So the time is 0, 1, 2, and 3. So maybe we have 1, 0, 1 at time 1, 1 at time 2, 1 at time 3. Cancel 2 and 4. Start at time 2. That is wrong. Oh, am I really this stupid?
Time limit exceeded. Test 7, sir.
What? What? Wait a second. Hold on a minute. How on earth? It's n log n.
Well done, sir. AC on problem D.
Darn. Ah. Oops. Okay. Well, at least I got it. Let's read this maybe. Yeah, we can't write a binary search, so we'll read it just for fun. Font of genealogy, currently studying particular genealogical structure, which consists of some people. In the structure, every person has both parents specified or none. Additionally, each person has exactly one child, except for one special person who does not have any children. Both parents specified or none. Additionally, each person has exactly one child. So it's a tree. It's like a backwards tree. The one special person is the root. And n, this denotes the child of this person. Okay. We say that A is an ancestor of B if A equals B, or if A has a child who is an ancestor of B. Yes. Person I is imbalanced in this case, so the person has both parents specified, and the total number of ancestors of one parent is at least double the other. Is at least double. Okay. I suppose. Count the number of imbalanced people in the structure and got k people total. However, he's not sure whether he computed it correctly and would like to check if there exists at least one construction with n people that have k imbalanced people total. Please help him find one such construction or determine that it does not exist. Oh, that's good. That's really funny, actually. I like it. So the problem is come up with a tree that has k unbalanced nodes. We'll go over solutions in just a minute. Just want to think about this for a second because I never really read it in contest. The most unbalanced you could get is a rope. How is a rope not unbalanced? Or a rope of length 3. It's funny, in this problem when they say ancestors, they really mean descendant. It's like inverted, kind of. Oh, also, like, this is the baby mom and dad, and then old grandpa, grandma. It's kind of funny. These are from the same meme. I get it. That's good. That's good. He's got the same hair color as these two people too. It's kind of funny. I didn't even notice that. So why in a rope is it not possible? Oh, because each person needs to have... Yeah, okay, so it's not just any tree. It's a tree, it's a, I guess, complete tree or whatever. It's a tree where every node has either 0 or 2 degree. So now, if you remove all the leaves, now it's any tree. Yeah, so there's that condition. So you remove all the leaves, now it's any tree. But then, if you have any tree, you can get up to n-1 nodes unbalanced. So you can just do a rotation here, and that makes that more balanced. Oh, that increased it by 2. Oh, you could put the other node over here. Is it at least half or exactly half? Or more than half? At least double. Yeah, so you can do binary powers of 2 stuff. Yeah, okay, so it's not too bad. All right, let's go over solutions to A through D and then some observations on F. That's what we'll talk about. Because I don't know enough E to explain it. Maybe I'll talk about what you can maybe think about for E. So A, man, this was as far as problem A's go, this was a hard problem A, I thought. Like usually, I don't know, usually A's are like 1 line of code or something. Very easy. So you want to find if you can change the question marks in some string so that there's exactly 1 abacaba. Okay. So you have some string. And then you want to change some question marks to see if there's going to be exactly 1 abacaba in the string. So since the bounds are tiny, what you can do is you can brute force where this abacaba is going to be. If you know where it's going to be, like let's say we know it's going to be here, then we have to fill these letters in so that it's A, B, A, C, A, B, A. So we can just like walk through and replace all of these question marks with a whatever letter they're supposed to be. And then for any question marks outside the range, the only important part is that we don't accidentally include another abacaba. So we can make these all Z's or something. And now if they're all Z's, then anything that contains this won't contain abacaba, which is what we want. Yeah, and then afterwards we can check if what we did worked. So this also works if there's like some abacaba in the string, we can just find it. To check if it works, you just like brute force each start position, then check the next 7 letters. So you can you can brute force where you want to put it and then check if that works. It's like n squared times 7 squared or something. That works, or n squared times 7 roughly. All right, cool. That's problem A. Problem B. He wants to send strictly positive integers to his friends. Oh yeah, this was interesting. So the cost is going to be like M is equal to N times A plus B minus C. So basically this B and C, the only thing that matters between them is their relative difference, which means you want this to be as close as possible to M. That way you can support the closest range between R and L. So we can brute force what this A is. We can just iterate through all numbers between L and R. And now if we know the A, then we know, like, we can figure out what this N is by plus or minus 1. So we want the N to be as close as possible to M so that it works. Once we know what A and M are, then we know B minus C. So we can just make, we can make this be whatever amount that we want, as long as the difference is small enough. Here is what the code looks like for that. It's pretty simple. So we have our L and our R. We also have this M, which we're given. And now below times is like how many times would you multiply A by some number in order to get some number that's less than M. So like what would the lowest possible N be? And this is what is the highest possible N. So it's one of these two. You have to special, this is in samples, but you have to special case if below times is equal to 0, then you don't want to count the lower version of it because apparently N has to be positive. So yeah, that's problem B. It's a little math heavy, I think, but not too bad. Problem C. Yeah, problem C. So C isn't too hard either, but all of these problems are like, I think a little harder than usual Div2, A, B, and C. Maybe not though. So the idea is that you have a bunch of flowers, each has like some A cost and then some B cost. So the first one you get will be like A1, and then you get B1, B1, B1. Then you have maybe an A2, and then a B2, 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 then an A3, B3, B3, B3. Maybe an A4 as well. So the first observation is that there's no reason for you to alternate between two B's. So like, let's say you're taking some of these B's and then some of these B's as well. That's never going to be a necessary thing to do. Instead, you can always just take all of one B's and then some A's. Because like, let's look at these two things. We chose to take this instead of taking this. Well, one of them is bigger or they're the same. If they're the same, let's just take this and then we're fine. So we could take that and then that's equivalent to taking these two if they're the same. If B1 is bigger, then we should take this instead of taking this and these two. And if B2 is bigger, then we shouldn't be taking these two either in the first place. We should just take 3 B2s. So you only ever want to take from one of these B groups, and then other than that, you're just going to take several A's. So what you can do is you can brute force which B group you're going to take from, and then you want to take all of the A's that are greater than that. So if you can count how many A's are greater than that, if you have like a tree set higher, or you have the A's sorted and you can binary search, then you can do that. You can also do a sweep, where you first sort all the flowers by A and then sort all of them by B in 2 different lists, and then you can sweep through. The thing to be careful for is if you would normally want to take this A, but you also want to take the A because it's greater than the B's, then like I guess you just have to be careful because you don't want to like double count it as buying it twice. But I'm pretty sure you should fail samples for that if you handle that wrong. So it should be pretty easy to work on paper. So that's the general idea for problem C. Problem D. Yeah, it's I guess I'm not a very trustworthy source to say it's an uninteresting problem, but it seems like a pretty interesting problem. Like, it seems like the observation is pretty boring and then the code is uninteresting after that. I feel, at least. But basically, you have this circular time zone. You have this day, really, split up into a bunch of hours, maybe like that. And then you're going to have something that happens every like 2 times each hour. Maybe it happens like this. It happens the same times every hour. And also these things are split by half hours. So these start points are half hour apart. So the basic observation is like, okay, well, we're splitting this by hour, but that really makes no sense. We might as well just split it by half hour. So let's do that. Okay, now we've split it by half hour. So now this just happens once every hour. Since from this point, everything is symmetric so far, what we can do is we can just look at just 1 hour instead of looking at all the hours. So I've drawn it like this. There's another case which is also possible, which is that this important time overlaps kind of like that. But that's just because it's circular, I guess, so it's not really too important. All right, so now you also have a bunch of events, and maybe your events look like this or whatever. And now you want to find, okay, for this white time, when can we place the white time so that we have to delete as few green events as possible? And to do that, what you can do is you can make the observation that, okay, the white time is going to start right after some green time ends. So let's say we have some white time that's like, maybe it's like this. What we can do is we can just slide it left until it's right before some green time. And if we do that, then it starts right after this green one ends. So yes, that's the proof of why we only need to check ranges starting right after some green dot. And then we also, like, handling it circularly is something you can either do with 2 times the phrase, or you can put everything in this twice. And then you can just query this next, like, cloned copy of the range, which would also have this imaginary one, this imaginary one, this and this or something. It looked like that. So now we would query this range here. So yeah, that's the implementation details. If you have C++, you can just like query how many things are in a range without compressing even, just with your ordered set, which would be nice to have. In Java, we don't have an ordered set, so you can write a implicit segment tree and implicit segment tree, and that will do it well enough. And then just be careful that like you don't forget to divide m by 2 in one of the many places that you need to. Okay, for problem E, yes, this is like inverse genealogy. I don't actually have a solution to it, but I have some idea maybe that might be helpful. So here's the idea. So the problem requires that you have a tree with some properties that every node either has 2 kids or it has 0 kids. Which means you have all of these leaf nodes which are special because they all have 0 kids. So let's like look at them in a different color maybe. So now one observation is that we can just get rid of all of these kids like this. And when I say get rid of, like, I mean consider them separately. Because if you have no kids, then like, I guess we know how many leaf nodes a tree is gonna have, right? A tree with n nodes, or a tree with, like, if it has n white nodes, then it will have n plus 1 green nodes. Like any binary tree will be like that. So yeah, that should be helpful enough, I think. So you know how many white nodes there are. Now, if you have n white nodes, you can make up to n minus 1 of them be unbalanced. So the reason you can do that is because, like, now once we've taken out these green nodes, we can make any tree we want with the white nodes. That's the main virtue of separating the tree like that. Once we can make any tree we want, then we can do like the following. So we can start with a rope that's very long. And now what we can do is we can make any number of nodes along this path be unbalanced. So if we want to get rid of this node, we can like get rid of it by putting it here. And basically we can like imagine how many trees this can hold. So if this is like, if we want to have 4 left over, this can hold 1 node, and this can hold, well, let's say this holds 1 node. Then this has 1, 2, 3, 4. So now this can hold 2 nodes. And now what we could do is like if we had it be like this, then this could hold 4 nodes, etc. So we can make all of these trees in a balanced way, and then we can like use increasing powers of 2. The issue is like if you want to represent 5, you can't use this 1 and this 4. So if you want to represent 5, you would do 1, 2, and then 1. And if we did that, then like all of these things are balanced, right? All of the green numbers that I wrote are balanced. The unbalanced nodes would be all of these. Yeah, okay. So that's that problem. Problem E. I suppose you also have the interesting case where you just have 2 nodes. In this case, this one needs to be unbalanced. So I guess that's a bit tricky. Yeah, and also the way I described it might not work actually. So my solution might not work because you might, like, without further thought, you might run into this in the subtrees that you wanted to be balanced, which would be an issue. So yeah, maybe that needs more thought. Okay, so for problem F, there are 2 versions. For the easy version, I think the intended solution is to binary search where all the answers become no, because once it's no for the first time, it'll be no after that. So then how do you tell if it becomes no? Or how do you tell if for like a given board it's yes or no? Let's draw let's draw an 8x8, I guess. 6x6. So we can color, like, a bunch of these squares don't matter, but these squares all matter. The red ones. And then also the green ones matter as well. So one thing you can notice is that you can color all red squares. You could like place kings on all red squares, or you could place kings on all green squares. But you can also do better than that. Like, it's possible that neither of those are possible, as I learned from my submit, but it's still possible to place enough kings. So this would be some example, maybe. You could do something like that. Yeah. And basically what will happen is you'll have some monotonic chain of like if you pair these things up, then if you pair them up like this, then you're gonna take at least one element, or you're gonna take exactly one element from each pair, if it's possible. So now the question is, like, can you take one element from each pair? And not only does each pair need to have one element available, but also if you ever take a green element, like if we ever take, let's say we take this element here, what that means is that we can't take this red one or this red one. So basically we have to take this green, and we also have to take this green, and then like transitively we have to take all of the greens in this, like in this square here. So these all need to be green. So anytime there's a green, we need to have green available for anything to its right or below it. So what that means is like anytime there's a red deleted, then like we can look at the problem twice. We can look at it first as like, are there any greens deleted that make it impossible? And then also, are there any reds deleted that make it impossible? Which means let's look at the reds that are deleted, and then if we have like a deleted red here, like maybe this is deleted, and then we have a deleted green in this subrectangle, that means it's impossible. Because we know if this red is deleted, we have to take this. We also have to take this. We have to take like every green thing in here. And if this is deleted, we won't be able to do it. You'd also flip this problem and solve it the other way as well. Like check if there are any greens. Like greens will force a rectangle of reds. So, but like you have this monotonic chain, right? So you've got this chain of things that like it goes up into the right at every step, and we want to know, is there anything that would make, like if some green is deleted, right, maybe this green is deleted here, is there anything that makes this impossible? So in this case, like there are no reds to the up or above or to the left of this green, which makes this fine, but this one here is an issue. Yeah, okay. So now how do we actually do this? Well, if you have two monotonic chains and you want to see if they intersect, this is a pretty common divide and conquer algorithm that you can do. You can also do like two binary searches in this case. So, or maybe it's not divide and conquer. Like, you can do divide and conquer to like maximize the area. But, that's not what we're trying to do. Well, I guess it is, right? We want to maximize the area between green and red. So yeah, so there's a divide and conquer strategy that would work. But also what you can do is if you have some green position here, the only time it would be illegal is if there's some red that is to the left of it and above it. So what we'd want to do is we would want to find the first red to the left of it. And if we have that red, we just need to see, okay, is it above it? And we know, like, we don't need to check anything farther left than this first one, because since the red chain is monotonic, they're going to go down from there. So if this first one is below it, then the rest of them will be too. So yeah, so that's how you could do F1. For F2, somehow you need to do that faster. I don't know how. Like you can't binary search and then you can't like binary search the answer, binary search how many queries and then answer them. You have to, it seems like you have to maintain this monotonic chain, but the issue is I'm pretty sure you can't just maintain the monotonic chain. And the reason for that is if you have this large chain and then you add like this point here, that changes the chain in a huge way, right? We've just deleted order n elements. And now if we delete this element, now all of a sudden we've added a bunch of new elements back into the chain. So you have to...
Problem D. Time limit exceeded test 7, sir. Problem F1. Wrong answer
Okay.
test 7, sir.
Well, stuff is starting.
Problem D. Wrong answer test 3, sir. Well done, sir. AC on problem A.
Yeah, okay.
Problem A.
So lots of announcements as things get judged.
Wrong answer test 1, sir.
Anyway, yeah, so that's the idea for problem F. Hopefully you enjoyed watching. Maybe some of the solutions were helpful. I don't know, probably not too much because I didn't solve too many of the hard problems. But yeah, that's all. The round was a little bit uncomfortably early for me, but hopefully if you live somewhere else, not in the United States, then it was at a more reasonable time, and hopefully you enjoyed the round. Yeah, that's all. Goodbye.